what if, like, the very foundation we use to reason about the world, I mean, the bedrock of geometry itself, wasn't as solid as we always thought? Welcome to this deep dive where, we tackle some of those really big, fascinating questions. And today, specifically for you, our listener, with, that sharp philosophical hind, we're diving headfirst into the epistemology of geometry. And we're going to be drawing from, like, the vast, rich landscape of the Stanford Encyclopedia of Philosophy.
And it's fascinating, isn't it? It's not just about those formulas and proofs you might remember from, like, school or whatever. Because for a philosopher, someone like you, the history of geometry, it's like this incredibly rich tapestry of, evolving ideas about knowledge itself, about how we know things. What does it even mean for us to say we're certain about something in geometry? How much does our intuition, like our gut feeling about space, shape our understanding? And how do those, like, perfect geometric ideals we work with, those perfect circles and triangles, how do they relate to the actual world, which is often, let's be honest, kind of messy? So those are some of the, like, deeper currents we'll be navigating today.
Exactly. I mean, that's what makes this so interesting. It's not just about shapes. It's about how we think. So our mission, if you will, in this deep dives is to really unpack, the major epistemological challenges and those often mind-bending shifts in our understanding of geometry, starting, way back with Euclid, who seemed so unshakable for so long, all the way to those revolutionary ideas that, like, emerged in the 20th century. We're going to be wrestling with the very nature of geometric certainty, the role of intuition, which can be tricky, that persistent problem of idealization, and that, like, always evolving relationship between the abstract, precise world of mathematics and the very tangible, concrete realm of natural science.
And, where better to start than with Euclid himself? Because for over 2,000 years, his elements, I mean, they held this incredible status. It was the gold standard, right? Like, if you wanted an example of, like, perfectly well-founded science, that was it. But, when we put on those critical philosophical lenses, which I know you will, some really fascinating and, frankly, thorny issues start to emerge.
Right, because on the surface, it all seems so clear and straightforward, those lines and angles.
It does. And one of the first places where, those eyebrows start to raise, for me at least, is right there in the definitions. Just take his definition of a straight line. He says it's a breadthless length, which, okay, I kind of get it. But then he also says the straight line is one which lies evenly with the points on itself. And, it sounds almost poetic, right? But for building, like, a truly rigorous, logically airtight system of knowledge, that phrase lies evenly, well, it's not exactly precise, is it? It feels like it's appealing more to a shared intuition that we all have about straightness rather than, like, a truly foundational, unquestionable principle.
Exactly. It's like, yeah, we all kind of know what he means. But for a philosopher, it immediately raises all those questions about, like, are you allowed to rely on these intuitive concepts when you're building what's supposed to be, like, a purely logical system?
Right. And this, like, lack of perfect precision, it has these knock-on effects throughout the whole system. For instance, one of the things Euclid states, which seems very basic, is that you can draw a line segment between any 2 points, which seems, obvious. But he doesn't explicitly state that this segment is unique. And again, intuitively, we all agree. Of course, there's only one straight line between 2 points. But for a truly rigorous, logically complete system, you actually need to prove even those seemingly self-evident things. And that missing statement, the missing postulate, it actually creates this, like, logical gap in the proof of his very first congruence theorem, proposition I.4, the one dealing with, proving that 2 triangles are equal. And this highlights how even these seemingly tiny, like, unstated assumptions can have these ripple effects, potentially undermining the entire structure.
Okay, now here's where things get really interesting, for me at least. And this is particularly relevant when we're thinking about the nature of proof, like what constitutes a proper rigorous proof. You mentioned congruence, proving that triangles are congruent. And that brings up the whole way Euclid deals with copying segments versus copying, like, angles or triangles. Theorem I.2, he very meticulously details how to exactly copy a line segment.
Right.
You use your compass and straight edge, and you do it step by step. But then in I.4, which needs you to copy an angle to prove the triangles are congruent, Euclid kind of just gestures at it. He basically says, yeah, you just pick up one triangle and put it on top of the other. And he doesn't really explain how you do that perfectly. And it makes you wonder, like, methodologically, why go through all that trouble for line segments in I.2, but then just kind of wave your hand at it when it comes to triangles in I.4?
You've hit on a really subtle point, but it's a fantastic observation. And it exposes this implicit reliance on what's often called the motion of figures in Euclid, this idea that you can, like, physically pick up a shape and move it around to demonstrate equality. And this became, a huge point of debate and discussion later on, especially within like the very rich intellectual traditions of the Arabic and Islamic world. They really scrutinized this unproven claim in I.4 about just copying triangles because it stands in such stark contrast to that careful step-by-step deduction in I.2. And it raises these really deep questions, like for a philosopher, about the very nature of geometric demonstration. Is it purely logical, or is it relying on some kind of like idealized physical manipulation?
So you have these issues with like the very definitions themselves and then this implicit reliance on physical manipulation. I mean, for a philosopher thinking about the foundations of knowledge, those are some pretty significant cracks. So what about the parallel postulate? I mean, it's the one everyone always talks about, that famously contentious issue.
Well, one way to think about book one, and maybe why the parallel postulate didn't seem quite as intuitively obvious to a lot of people, is to think of a straight line as having like a direction. If you look at it that way, then the parallel postulate is basically saying that lines which like cross a given line at equal angles, they're kind of pointing in the same direction, and so they'll never meet. But it's important to remember that this is an interpretation.
Right.
It's a way to make sense of it, but it's not something Euclid explicitly lays out and rigorously develops. It takes quite a bit of conceptual work to make this idea of direction precise within his system. And this lack of immediate clarity, I think, is exactly what made it such a philosophical sticking point for centuries.
Okay, so direction is one way to think about it. What about the concept of distance? I mean, that seems fundamental to geometry. Was that a primary foundational idea for Euclid?
It's surprising, but no, not really. Euclid doesn't start by saying hey, a straight line is the shortest distance between 2 points. That idea comes later. His primary concept related to length, like the starting point, is this notion of equality of segments. Think about the radii of a circle. They're all equal. And common notion 4, one of his basic assumptions, states that if you can perfectly superimpose 2 segments so they coincide, then they're equal. But then, and this is in I.4 again, that problem child, he uses the converse. He says, okay, if 2 segments are equal, then you can make them coincide. And for a philosopher who's really concerned with logical rigor, that feels a bit circular, right? It's you're relying on the very notion you're trying to establish.
Yeah, it does feel a bit wait, are you assuming what you're trying to prove? That kind of thing.
Exactly. It's begging the question, However, to be fair to Euclid, he does introduce the triangle inequality in proposition I.20. This states that, any 2 sides of a triangle added together have to be greater than the third side. And this result, it does lay some groundwork for the idea that a straight line is the shortest path between 2 points. But it comes out as a consequence within his system, not as a fundamental starting point. And that distinction between what you assume and what you derive, that's crucial for philosophical analysis.
So we have these definitional issues, the reliance on motion, and then this tricky business with distance. What about the plane itself? Euclid defines that, but it seems like his definition there is just as open to philosophical scrutiny as his definition of a straight line.
Oh, absolutely. He says a plane surface is a surface which lies evenly with the straight lines on itself. And again, we have that phrase lies evenly, which, doesn't exactly scream rigorous mathematical criterion, does it?
Not really, no. It's come on, Euclid, you could do better than that.
Right. And what's fascinating from a philosophical perspective is that after giving that definition, the concept of a plane pretty much disappears for the next 4 books, which are all about plane geometry. It's almost like the definition isn't really doing any work within his own system. And then when he finally gets to solid geometry in book 9, he tries to establish some basic properties of planes, a line can't be partly inside and partly outside a plane, or that intersecting lines have to lie in a plane and that 2 planes always intersect in a line. But again, these are more claims, things he just asserts as being true, seemingly based on intuition, rather than rigorously proven theorems derived from his initial definition. And this, again, raises questions about the deeper, unstated assumptions that are guiding his work.
So even these basic building blocks of geometry, lines and planes, have these deeper issues lurking beneath the surface. And this makes, I think, Gauss's later observation about proposition I.4 even more relevant.
Oh, totally. So Gauss, in some of his unpublished remarks, pointed out that to actually rigorously prove that those two triangles in I point 4, ABC and ABC, that their vertices have to coincide, you need to explicitly use the fact that they both lie in the same plane. And to do that properly, you need a really solid working definition of a plane, something Euclid kind of glosses over in those early books. And this shows how even what seems like a minor oversight can reveal these deeper foundational weaknesses when you subject it to that intense, logical scrutiny.
Okay, let's shift gears a bit here. Euclid's work, despite, all these issues we talked about, was celebrated for centuries because of its beautiful, deductive structure. But it relied heavily on diagrams, those visual representations. So how did that aspect of his work, like the reliance on diagrams, hold up under later philosophical scrutiny?
Well, for centuries, like you said, Euclid was praised for having this perfect, deductive presentation. But then starting around the 18th century, you have this rise of algebraic methods, what some people call the arithmetization of mathematics. It was this push to ground mathematics in the security of numbers, the certainty of algebra. And as that happened, diagrams started to fall out of favor. They were increasingly seen as mere visual aids, helpful but not essential. The real emphasis shifted to a purely logical presentation, based on explicitly stated axioms and formal proofs. And this movement, of course, paved the way for the groundbreaking work of Hilbert, which we'll get to later. But this shift in emphasis, away from diagrams and towards pure logic, it reflects a broader philosophical trend towards formalism in mathematics and away from a reliance on visual or spatial intuition.
But that wasn't always the view, right? Philosophers like Kant actually saw Euclid's reliance on diagrams as a real strength. It fit perfectly within his whole epistemological framework.
Yeah, absolutely. Kant argued that mathematical proof, at its core, relies on what he called the construction of concepts and intuition. And he saw Euclid's method, showing you how to actually construct a geometric object, like in that very first proposition where he constructs an equilateral triangle. Kant saw that as absolutely crucial. Because for Kant, just analyzing the abstract definition of, say, a triangle, that wasn't enough for proof. You needed to appeal to a concrete instance, either in what he called empirical intuition, like an actual drawing, or in pure intuition, which is a mental visualization, but one that's grounded in the inherent structure of our minds. And then you could build upon that construction, using the postulates and axioms to arrive at new results.
So for Kant, that diagram wasn't just a helpful picture. It was fundamental to the very act of doing mathematics, right?
Yeah.
It provided that necessary link between the abstract concept and our intuitive understanding of space.
Exactly. It gave you that concrete instance that was essential for what he called synthetic a priori knowledge. This is how he classified geometric truths. They were truths that were independent of any specific sensory experience, so they were a priori, but they were also informative about the world. They weren't just empty tautologies, so they were synthetic. But even this view, this Kantian perspective, it faced its own challenges and criticisms. And one of the most famous ones targets that very first proposition of Euclid, the one about constructing an equilateral triangle.
Yeah.
Critics pointed out that Euclid never explicitly states a continuity principle, something that would guarantee that those two circles he draws will actually intersect at a point C.
Right, so just drawing it and saying, hey, look, they intersect, that's not really logically airtight, is it? Especially if you're working within a purely deductive system. You need that underlying principle that guarantees the continuous nature of those geometric objects. It challenges that idea that intuition alone can guarantee the validity of these constructions.
Yes, precisely. It highlights that potential gap between what we see, even in our minds, and what we can rigorously deduce. But as Manders, the philosopher of mathematics, has pointed out, this objection might be missing some of the nuances of how diagrammatic reasoning actually functioned in Euclid's Elements, at least in those early books. He suggests that there's this, careful and deliberate distribution of roles between the textual propositions, which give you that exact general information, and the accompanying diagrams, which offer what he calls co-exact information. So the diagram isn't just a passive illustration, it's an active part of the reasoning process. It has its own, implicit rules of manipulation, ways of extracting information that guide the entire deduction.
That's a fascinating way to think about it. It's not just a visual aid. It's like this integral part of the logical argument itself operating under its own set of rules.
Exactly. And to see how crucial these implicit rules are, you just have to look at Klein's famous or infamous pseudo-proof, where he tries to prove that all triangles are isosceles. The trick in that proof is that he pulls information from a generic diagram in a way that violates the fundamental rules of Euclidean reasoning, the implicit rules we were talking about, and that leads him to this completely false conclusion. And this is also why it's worth considering Euclid's postulates themselves. They can be interpreted not just as these abstract, Hilbertian axioms, those purely formal statements, but more as practical rules of construction that guide how you're allowed to manipulate those diagrams. It's really significant that the Greek word for a mathematical proposition was diagramma, which strongly suggests this deep historical connection between geometric reasoning and visual representation.
So geometry starts off deeply entwined with visual thinking, with this hands-on manipulation of these concrete representation, those diagrams themselves, acting as a form of, intuitive logic.
Exactly. But as geometry evolved, especially in the 19th century with this huge push for greater rigor, there's this noticeable move towards a more abstract kind of edifice. You have to make those underlying assumptions really explicit and then scrutinize them logically, independent of any visual aids. The diagram, while still really valuable for building intuition, had to take a backseat to these more abstract, relational methods for analyzing those theoretical foundations.
Okay, and this brings us to a really crucial distinction, the one between synthetic and metrical geometry. So could you break those down for us? What do they mean, and why did this distinction become so important in, the overall development of geometric thought?
Absolutely. Let's start with purely synthetic geometry. So think of it as a geometry that begins with these really fundamental non-numerical concepts like straightness or flatness, and it mainly relies on what are called incidence properties, which basically describe the ways that, points, lines, planes, how they relate to each other. Do they intersect? Does one contain the other? And synthetic geometry tends to resist defining distance as a primary concept. It doesn't want to reduce those fundamental geometric statements to purely numerical relationships, although it can certainly incorporate coordinate geometry later on as a kind of development built upon those foundations.
Okay, so it's more about those essential relationships of connection and intersection without immediately jumping to measurement.
Exactly. Now, on the flip side, you have metrical geometry. And this one takes distance as its primitive notion, its fundamental building block. In this framework, you can directly compare line segments based on their length, and congruent figures are defined as having corresponding sides that are equal in length. And the transformations you're allowed to do in metrical geometry, those are the ones that preserve these links. So things like rotations, translations, and reflections, but also similarity transformations, which produce scaled versions of figures while still keeping the shapes the same, those are usually included in metrical geometry too.
And it sounds like there was this tension, almost a debate in the history of geometry about which of these approaches, synthetic or metrical, should be considered more fundamental.
Absolutely. There was this back and forth. And elementary geometry in the Western tradition, it kind of stumbled towards making distance this primary concept while also trying to hold on to that visual, intuitive emphasis on straightness that it inherited from Euclid. And that often led to, let's be honest, a kind of muddled understanding of the logical implications of each approach. But it wasn't all bad. This confusion, as the text calls it, wasn't entirely unproductive. You have John Wallis in the 17th century who was defending the parallel postulate. He recognized this deep equivalence between, on the one hand, Euclidean geometry as we know it with the parallel postulate, and on the other hand, a system of geometry that doesn't include the parallel postulate but does include the independent assumption that you can have similar figures of any arbitrary size. This was a big insight because it acknowledged a really profound connection between these two seemingly distinct aspects of geometry, parallelism and the ability to scale figures.
That's a really cool connection, right? The ability to make scaled copies of shapes being tied to this fundamental property of parallel lines. It makes you think there's this deeper underlying structure at play.
There is. And later in the Encyclopédie méthodique, D'Alembert defines geometry as the science of the properties of extension. So he's focused on bodies, surfaces, and lines as basically extended and figured. He believed that the fundamental principles of geometry were self-evident, so he wasn't too worried about rigorous axiomatization. He even defines parallel lines based on this idea of equidistance, and he says straight lines are just the shortest path between 2 points, which is definitely a metrical approach.
So he's leaning into that more intuitive measurement-based understanding of geometry, really emphasizing its connection to our physical experience of how things are extended in space.
Exactly. He's grounding it in our everyday experience. And then you have Legendre, who appreciated what Euclid was trying to do, but he felt like the rigor had been kind of, compromised over time. So in his book, The Éléments de Géométrie, he wanted to restore that lost rigor, and he did this by really embracing a metrical viewpoint. He even takes algebra and the theory of proportions as, given foundational tools. He explicitly defines geometry as the science that has as its object the measure of extent, and he says a straight line is just the shortest path. But even with all his efforts, his attempts to prove the parallel postulate, and he tried many times, ultimately failed. And you could even argue that he ends up introducing even more unstated assumptions than Euclid did.
So even with these best efforts to put geometry on this firm foundation of distance, they weren't totally successful.
They weren't. Even Fourier, when he was talking with Monge, explored the idea of starting with distance as the absolutely fundamental concept, and then trying to define things like spheres, planes, and lines based on this idea of equidistance. And while this did provide definitions for concepts that were a bit shaky in Euclid, it ultimately highlighted this need for a more consistent and rigorous basis for metrical geometry as a whole. And I think this growing discomfort, this search for a better foundation, probably played a huge role in creating the right intellectual climate for those radically new geometric ideas that popped up in the 19th century.
So by the early 1800s, there's this growing awareness that the foundations of geometry, especially when you approach it from a metrical perspective, really needed a serious overhaul. And this kind of intellectual ferment, this awkward position, as the text calls it, that really sets the stage for both projective geometry and non-Euclidean geometry to take root and flourish.
Exactly. It's like the old foundations are shaking and people are starting to look for something new, something more solid, more adaptable.
Which leads us to projective geometry. Now, it's often described as being more fundamental, more general than Euclidean geometry. So what is it about projective geometry that gives it this special distinction?
So in the 19th century, a lot of mathematicians started to see projective geometry as capturing those absolutely essential invariant properties of the straight line. Things like the fact that any two distinct points uniquely determine a line, and that any two distinct lines that lie in the same plane, they either intersect at a single point or they're parallel. But projective geometry does this while intentionally throwing out those metrical concepts, things like distance and angle. It's getting at the essence of straightness without getting bogged down in measurement. Now, you can trace the origins back to the 17th century to people like Desargues and Pascal, but it really gained steam with Poncelet's book in 1822, the Traité de propriété projective des figures, and he really presented it as this distinctly non-metrical geometry, which was a bold move.
So projective geometry is let's just strip away all those notions of measurement and focus on the core relationships, connection, intersection, incidence.
Exactly. And Poncelet showed how powerful this approach could be. He demonstrated the importance of what are called projective transformations. These were mappings that take lines to lines, but they don't necessarily preserve distances or angles. Think about projecting a shadow. The shape changes, but the lines are still lines. And later, Chasles came along and gave those ideas a more rigorous, formal treatment. He emphasized the fundamental invariance of what's called the cross ratio. It's a specific ratio you can calculate for 4 collinear points, and it doesn't change, even if you do a projective transformation. So it's highlighting a property that's even more fundamental than individual distances or angles.
Okay, now this seems a bit strange at first, right? Because you're saying projective geometry is non-metrical, but then its key invariant, the cross ratio, is actually defined using distances. So how do you square that circle?
That's a great question, and it caused a lot of head-scratching back then. It seemed paradoxical, how can you be non-metrical and yet rely on a concept that's based on measurement? And this foundational issue, it really bothered Carl Georg Christian von Staudt. He wanted to put projective geometry on a truly independent, non-metrical foundation. So, in the mid-19th century, he dives into this really deep and challenging project to build projective geometry from the ground up, completely free from any reliance on Euclidean metrical concepts.
So how did he pull that off? It sounds super tricky.
It was a massive undertaking. His work is notoriously dense and difficult, but his key insight was this. He realized that projective transformations could map any ordered triplet of points on a line to any other ordered triplet, and they could map any ordered set of 4 points that don't lie on a line to any other such set. But they couldn't map just any 4 points on a line to any other 4 points on a line. There was a constraint. And that constraint essentially is the cross ratio. So he meticulously studied these collinear quadruples and the transformations that preserve their relationships, trying to define the cross ratio purely in terms of these projective transformations, without mentioning distance. And while his work was like insanely difficult to follow, it strongly suggested that, yes, you could build projective geometry from scratch without relying on Euclidean concepts. And then along comes Felix Klein, and he provides this amazing clarification. He shows that von Staudt's abstract theory, if you combine it with the basic notion of Euclidean distance, it actually reduces to the familiar metrically defined theory of cross ratio. So he built this bridge between the seemingly non-metrical and the metrical.
So Klein showed how those seemingly metrical aspects could be, like, smoothly incorporated into von Staudt's purely projective framework.
Precisely. He connected the dots. And after all this foundational work, you have Luigi Cremona, who writes the first really readable textbook on projective geometry in 1873, the Elementi di Geometria Progettiva. And after that, boom. Projective geometry explodes in popularity. It's recognized as a fundamental, essential classical geometry in its own right. And its basic elements are points, lines, and planes, often considered within this three-dimensional space, math BR, but with this extra plane at infinity added in. And this addition is brilliant because it ensures that any two lines in a plane will always intersect, either somewhere in the finite part of the space or at a point on that infinite plane. So it unifies the treatment of parallel lines and intersecting lines. And the transformations you're allowed to do in projective geometry are the ones that preserve incidence, so those relationships of points lying on lines, and crucially, they preserve the cross ratio. And these transformations, they can move any point to any other point, any line to any other line. So no particular point or line is special, they're all treated equally.
Okay, so it's abstract, it's general, but it also has this like really elegant way of handling those fundamental relationships.
Yeah.
And this level of abstraction, this generality, it had real practical benefits, right? Like it actually simplified the study of other areas of geometry.
Huge benefits. For example, projective geometry provided this incredibly elegant and unifying framework for studying conic sections, ellipses, parabolas, hyperbolas. It showed that all those non-degenerate conics are actually projectively equivalent. You can transform any one into another using projective transformations. So they're all just different aspects of the same underlying projective entity. And when you translate all of this into the language of algebra, projective geometry becomes absolutely indispensable for studying algebraic curves of any degree. And you can extend this to higher dimensions to study algebraic surfaces. This success in simplifying and unifying huge chunks of geometry really solidified the importance of having a non-metrical geometry, one that's grounded in those fundamental concepts of the straight line and those incidence relationships.
And you mentioned something really interesting earlier, this concept called duality in projective geometry. Could you unpack that a bit? Like, what does that mean, and why did it spark so much philosophical interest?
Duality is one of the coolest things about projective geometry. So imagine you're working in two dimensions. The principle of duality basically says that you can systematically swap the roles of point and line, and you also swap related terms like coincident, which means a point lying on a line, and concurrent, which means lines passing through a point. And here's the amazing thing. If you take any valid definition, any theorem, any proof in projective geometry, and you do this swap, you get a new statement that's also valid. It's like this mirror image that's equally true. And in three dimensions, the duality is between point and plane. So every concept, every theorem, it has this dual counterpart. And this inherent symmetry, it really got people thinking. Cremona, for example, he saw duality as this fundamental law of logic, something built into the very fabric of how we think about space. But it also raised some interesting challenges for our intuition. Like, it's kind of hard to wrap your head around the idea of plane being made up of lines. And then you have this question about dimensionality. Is space two-dimensional or three-dimensional? Well, it kind of depends on whether you think points or lines are the fundamental building blocks.
So it's like projective geometry is pushing the boundaries of how we think about these basic geometric ideas and their relationships. It's not just about the math, it's about the philosophy of space itself.
Exactly. It forces you to re-examine those fundamental assumptions. And then building on all of this, you have Klein's revolutionary Erlangen program, which gave us this entirely new way to define and classify geometries using these concepts of group actions and invariants. It really reshaped the landscape.
So how did Klein's Erlangen program fundamentally change how we think about geometry?
So picture this. It's 1872, and Felix Klein delivers his inaugural lecture at the University of Erlangen. And he drops this bombshell, this incredibly elegant and powerful idea. He says, look, a geometry should be defined by specifying a space and a group of transformations that act on that space. And the key point, the thing that makes it a geometry, is that the fundamental properties of that space, the things you care about, those are the properties that stay the same. They remain invariant under all those transformations. And with this framework, this really simple but profound idea, he showed that tons of different geometries, including the familiar Euclidean geometry, those new non-Euclidean geometries we talked about, and others like inversive geometry, birational geometry, affine geometry, they could all be understood as special cases of projective geometry.
So it's like he created this hierarchical structure with projective geometry at the top, and then all these other geometries kind of branching out from it.
Precisely. He saw real projective geometry as the most fundamental of the classical geometries. It's all about real projective space and the group of all those projective transformations acting on it. And the things that stay the same under all those transformations, like points, lines, curves of a certain degree, and crucially, the cross ratio, those are the things the projective geometry studies. But then he had this other brilliant insight. He realized that if you start adding specific geometric configurations to the projective space, like say you pick a specific conic section, then the subgroup of those projective transformations that will keep those configurations unchanged, that subgroup gets smaller. And that smaller group defines a new, more specialized subgeometry with its own set of invariants. So by adding stuff, you get a smaller group and a more specialized geometry. And the reverse is true too. If you make the group bigger, then the set of things that stay invariant gets smaller.
That's a really neat way to think about it. It's all about how much freedom you allow those transformations to have.
Yeah.
And this perspective, this Erlangen program, it actually helped resolve that earlier issue we talked about, right?
Yeah.
The one about how you define the cross ratio, which seems metrical within a geometry that's supposed to be non-metrical.
It did. It gave a really clear explanation. So Klein drew this analogy with how we define and measure length in Euclidean and non-Euclidean geometry. In those, you have these groups of transformations, rigid motions, similarities in Euclidean geometry, and isometries in non-Euclidean geometry. And these groups all preserve the concept of a straight line. Any point on a line can be moved to any other point on that line. So to measure lengths, what we do is we arbitrarily pick a fixed line segment and say, okay, this is our unit of length. And then we can measure other segments because the allowed transformations won't let you squeeze a segment into a smaller portion of itself. That invariance under the group action, that's the key to measurement.
I see the parallel. So you need a unit of measurement, and that unit is essentially defined by what the group of transformations doesn't allow you to do.
Exactly. And building on von Stout's work, Klein argued that the same principle applies to the cross ratio in projective geometry. The full projective group preserves straight lines, and you can map any 3 points on a line to any other 3 points using a projective transformation. But you can't just map any 4 points on a line to any other 4 points. The cross ratio puts a constraint on that. So Klein said, look, a fixed set of 4 points on a line, that can act as our unit for measuring other cross ratios. It's like a ruler for cross ratios. And he even showed how you can take any 4 points on a line and use a projective transformation to map 3 of them to 0, infinity, and 1 on the number line. And then the position of that 4th point, that gives you the value of the cross ratio. So it's a really neat way to see how a seemingly metrical concept actually fits perfectly within a non-metrical framework. In this Kleinian perspective, length is like a 2-point invariant in Euclidean and non-Euclidean geometry, while the cross ratio is fundamental 4-point invariant in projective geometry.
Okay, so Klein's Erlangen program wasn't just a way to organize geometries. It was a deeply insightful principle for understanding their fundamental nature.
Exactly. It shifted the focus away from the specific geometric objects and axioms of each individual geometry and put the spotlight on the group of transformations that defines its structure and on those properties that stay invariant under those transformations. It was a much more abstract and structural way to think about geometry as a whole.
And this move towards abstraction, this focus on axioms, it really fueled a renewed interest in, the formal axiomatic foundations of geometry, especially for projected geometry in the late 19th century.
It did. There was this drive to make everything absolutely rigorous. And people like paths.